Okay, so what are we talking about? So last lecture we were discussing, well, the set of continuous maps between topological spaces X and Y. And, well, why do we care about that? Well, because Hilbert spaces, the central examples, are function spaces, and this is, of course, on metric and Hilbert spaces, so that's a kind of a lame motivation. You're here after all, so you must care about Hilbert spaces. But as I explained 2 lectures ago, I guess these are also very important in functional analysis and physics in general. It's not clear, however, how to put a topology on these sets. So that's not meant to be obvious, right? These aren't obviously topological spaces in a useful way. But, I mean, it should be plausible, perhaps, that we can make them topological spaces if you think about the following sort of example. So if I had a continuous map just from the unit interval to itself, well, there's a more geometric object associated to that, which is its graph. Right, so that's as a subset of 0, 1 squared, and it's a closed subset. So if I ask you to think about, you know, what is an open neighborhood of f in CTS xy, well, there's kind of a reasonable answer to that question, right? So, you know, what constitutes a sort of set of functions close to f? Well, I could take an open subset of that square around f, or rather around the graph of f. So let's call that, say, u. So if I took u in 0, 1 squared open with gamma f contained in u, well, it would make sense to call another function g close to f if the graph of g lies in that open set. Right? I think that sort of fits with what we would imagine it means for the graph to be close to the graph of f. So I could sit f inside the set of functions g such that gamma g is contained in u. That's a subset of CTS xy. Right? Okay, so at least in this special case, maybe we can believe that this would give rise to a topology on the set of functions. But the challenge in general is, well, that's sort of special because both of the spaces involved are compact, for instance. So maybe we want to do better and put a topology on this in general. And then, well, it's not sort of clear where to start in doing that. What I explained last lecture was that there's one identity we can take as sort of the guiding star for figuring out exactly what the topology should be, and that was this identity, which was that, well, maybe we want a topology on that set such that the following identity holds. Right, for any spaces z and y, and actually it turns out that this is sort of only reasonable to expect if x is, well, last time I was discussing the case where x was compact in Hausdorff. There's a weaker condition, which is local compactness, I'll discuss today. And actually this holds also in that generality. But okay, so I haven't explained this yet, but this will be somehow a focus point of the lecture. Okay, so we want a topology on that set of functions such that for x compact Hausdorff at least we have this identity. That's somehow because otherwise how the hell would you understand continuous maps into this thing if you couldn't write it in terms of something else? That's sort of one way of putting it. A slightly more sophisticated way of putting it is that this identity actually reduces the conceptual landscape from containing both products and function spaces to actually just containing products, because this identity, if you sort of get used to it, tells you can reduce everything you want to know to some degree about that thing to just knowing about the product. So that's encapsulated in this word adjunction. Okay, so this is called the adjunction property. So that's where we got up to last time, and what we figured out was, just assuming that identity worked, we figured out at least some of the sets which had to be in the topology, which was that for X, compact Hausdorff and Y arbitrary. This set had to be open in the topology. For K compact and U open. Now, it probably looked a bit complicated, and it's not sort of meant to be that there was a strong conceptual reason that you could see in the derivation last time for why you would necessarily find these sets particularly appealing, but nonetheless you're supposed to believe that we do arrive at these sets, and we'll get to the intuitive content a bit later. Okay, so those things have to be in the topology in the precise sense that in order for this identity to work, those things have to be open. All right, so that was what we figured out last lecture. Now what I'm going to do is, we'll take this as a starting point, and without any acrobatics of sort of assuming something and then trying to figure out what was going on, we'll just clear the slate. We take this as our inspiration and we define a topology conditional on nothing. So this is all now completely sort of fully constructed. And then we'll prove this identity. That's the aim. Okay, so maybe I'll make the definition. Well, first I need to define the concept of a subbasis. So we've discussed the concept of a basis. The basis had some conditions, right? It was if you just take a set of subsets of a set and it satisfied some conditions, then the set of all possible unions of things in that set gives a topology. That was what a basis was. But there were some conditions, right? I couldn't just take any set of subsets. But in fact, you can start with any set of subsets of a fixed set X and generate a topology with no conditions placed on the sets whatsoever. And that's the idea of a subbasis. Okay. So the exercise is that. So what do I mean by generate? I need to make that precise. So given a family of topologies, right, so a fixed set X, but an indexed family of topologies. So each one of those TIs is some subset of the power set of X. Then the set of all subsets of X which are simultaneously open in every one of those topologies, which is that set, is a topology. Okay, so it's just an easy check if you think about it, and the properties of intersections and unions. Okay, well that means that I can take any set and generate a topology, because I just take the set that I'm interested in, I take all topologies containing it, and then I intersect all of them. Right? So notice that this intersection is by definition the, let's say, definition. Okay, so take a set X and take a set S of subsets of X. So curly S is a subset of the power set of X. And take a topology T on X. Then we say that that collection of subsets is a subbasis for that topology. Well, let's say for the. So I'm given T, I'm given S. S is a subbasis for T. If for every topology, well, so if the sets in S are open, so that is to say S is contained in T, and for any topology T prime on X, which contains S, we have T contained in it. So that just says that T is the smallest topology which contains S, right? So given a set S, we can ask, is it a subbasis for some topology? And the answer is always yes. Okay, so if S is any set of subsets of X, then the so I'm just deciding which order to put this. So let's say then the set T of all unions of finite intersections of elements of S is a topology, and S is a subbasis for T. In fact, it's basically the same statement. T is the intersection over all topologies containing S. Okay, so there's multiple statements there. Let me focus on this one first. So we're just given some set of subsets of X. First step, form the set which consists of those sets which can be expressed as a finite intersection of elements of S. I include the empty intersection, which is the whole set. Okay, just like an empty union is the empty set, where you don't intersect, where you don't union anything. The intersection of nothing, that is indexed by nothing, is the whole space. Okay, so take your set S. First, sit it inside, we could call it S prime. So those are all the things which are finite intersections of elements in S. And then take the set of all arbitrary unions of things which are in S prime. Okay, that's T. Okay, so that's a topology. So you need to check that's closed under finite intersections and arbitrary unions. Arbitrary unions, I mean, that's by definition. Finite intersections, that's a little check. Okay, so that's a topology, that thing constructed in that way. And, well, let's convince ourselves of the inclusion that way. Suppose something's in T. Well, then it's a union of things which are finite intersections of things in S prime, in S. So if I had a topology Q which contained S, well, the topology is closed under finite intersections and arbitrary unions, so it better contain all the things in T. right? So T is contained in the right-hand side. And if you think about it, the only thing in common to every possible topology is exactly the sets I described. Okay, so there's some details to check there, but so I'm leaving that as an exercise. So that's a way of getting from any collection S to a topology. Right? First take finite intersections, then close under arbitrary unions. Okay, so take two topological spaces, X and Y. Look at all pairs consisting of a compact subset K of X and an open subset U of Y, and then form this set SKU. So that's the set of continuous functions from X to Y, which happen to send the subset K into the subset U. That's some collection of subsets of CTS XY. Any collection of subsets generates a topology. So maybe I should, we call T topology generated by S. Okay, so take that set, take the topology that it generates, that is the smallest topology which contains it, and that's by definition the compact open topology. Right? So, well, as we just described, the open sets in the compact open topology are therefore arbitrary unions of things that look like SK1 union, sorry, U1 dot 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 SKN UN for some compact KI and some open UI. All right, well, if I can get a topology from any collection of sets, I mean, that doesn't, you don't expect necessarily anything good to happen if you just pick some random sets. So the challenge is then to prove that anything interesting works for this topology. Okay, any questions so far? All right. Okay, so let me prove this identity. Well, okay, so now I have to explain locally compact, don't I? All right. Okay, so let's discuss local compactness. Well, R is locally compact, for instance, as we'll see. Okay, so this is a rather big generalization. Before last lecture, when I stated it, it was just for X compact, say for intervals. Now it's going to work for R and Cartesian products of R with itself. So this is a significant upgrade. So it's worth, maybe a little bit more effort. So if X is locally compact, if, well, around every point it sort of looks compact. So if for every X in X, there exists U in X open and K in X compact with X in U contained in K. Okay, I can't just say like there's a compact subset of X which contains little x, right? Because if X was Hausdorff and I just take the singleton X, well, that's finite and discrete and therefore compact. So that would be an empty definition. And that's not really what I want, right? What I want to capture is the situation with what happens with R. That's sort of the point of this definition. So Rn is locally compact. Well, why is that? Well, because if I take an x in Rn, that sits inside some open neighborhood like that. Right? I mean, that's, if you like, that's a basis for the product topology, as we discussed. So there's some open neighborhood like that, and that guy sits inside a product of closed intervals. And well, that's a product of, in compact spaces, and therefore compact, as we discussed. That's Heine-Borel. Right? So that's open, and that's compact. So Rn is locally compact. Not everything that works for compact spaces works for locally compact spaces, but some of the things do, and it's sort of significantly more general. So we need just a few properties of locally compact spaces. Well, maybe I should say compact implies locally compact, right? Just take U equals K equals X. So compact implies locally compact. All right, so maybe we'll just say it out loud while I'm erasing. So if you take a closed subspace of a locally compact space, I claim it's locally compact. Why? Well, take a point of your closed subset, pick an open neighborhood of it and a compact neighborhood of it in X according to that definition, intersect both U and K with your closed subset. Well, since closed subsets of compact sets are compact, that works. Okay. A bit less trivially. So if X is locally compact and Hausdorff, it's regular. I'm going to define this in a second. So this occurred in the notes, but not in the lectures yet. Or maybe I mentioned briefly. So regularity and normality are sort of conditions related to Hausdorffness, but stronger. So a space X in which all points are closed is, there's two definitions, regular and normal. So it's regular if points can be separated from closed sets, and normal if closed sets can be separated from all other closed sets. So more precisely, so take my space X, take any point, and take any closed subset. If for any such configuration, so X is not in A, so if for any A closed, X not in A, there exist U and V in X open and disjoint with X in U and A contained in V. But so remember, Hausdorffness said if I have 2 points, so it's a special case, if you like, as long as points are closed. If I have 2 points, then I can find an open neighborhood, pair of open neighborhoods which separate them. And this says I can do the same, but if where one of the pair is instead a closed set, that's not automatic from being Hausdorff, incidentally. And normal if for any pair of closed subsets with A intersect B empty, the same. So there exists U and V, open and disjoint, that is having empty intersection, such that A is contained in U and B is contained in V. All right, so I left some exercises in the notes. So metric spaces are normal. Well, maybe I should say so. Normal implies regular. Right? If you know this for all closed subsets, you know it for points. And that implies Hausdorff. Okay, so there's strengthenings of the Hausdorff condition. Metric space is normal, therefore regular. We discussed that they're Hausdorff earlier. So I'll provide a proof for that in the notes sometime soon. And a compact Hausdorff space is normal. So, I mean, that's a little bit of a tweak on a proof we already did. Okay, so I realize there's lots of definitions today. Okay, so the main point of all of this is this statement. Compact Hausdorff implies normal. So if you can separate two points, any pair of points, in a compact space, you can separate any pair of closed sets. Okay. All right. So now I'm making the claim that if you weaken the compactness, so it's only locally compact, still Hausdorff, you don't get normal. So it's not true that a locally compact Hausdorff space is normal, but it is true that they're regular. Okay. So, all right, so here goes. Any questions about the definitions? You might ask, why do we care? Well, that's going to be the crucial point in proving this. Let's take the configuration that we have given to us that we need to provide open neighborhoods for. Sorry, it's become a B. So X and B. All right. Well, we're going to reduce to this exercise that compact Hausdorff implies normal, which reduces to an argument that we saw sort of earlier, essentially. So what are we going to do? Well, we're going to take our point and find this configuration around it and then try and use that. Okay. So choose U, X open, K compact, with X in U contained in K. All right, so we have something like this. So there's X, there's K. So notice that the space is Hausdorff and K is compact, so it's closed. And I've got some open neighborhood U containing X contained in K. And I've got a B which is closed and doesn't contain X. Okay, so some part of B lies outside of K and some part of B lies inside K. All right. Now, so using this, so K is compact, it's a subspace of a Hausdorff space, so it's Hausdorff, and therefore K as a topological space is normal. So focusing on K, on the closed set B intersect K and the point X, we can find an open neighborhood. I'm calling it V. VW, open and disjoint in K. With X in V and B intersect K contained in W. All right, that's just what normality gives me. Well, I mean, it's regularity, I guess, but we know compact Hausdorff implies normal and therefore regular. So here's my V. Well, let me draw it a little carefully because I want it to meet the boundary. Right, this V, it's open in K. That means it's the intersection of some open set in X with K, whereas U was open in the whole space, right? So that's why I draw it actually looking open. So that's V. And then there's something here, let's call that W. Okay. Well, there's some open subsets of X which intersect to give those things, by definition of the subspace topology. All right. So okay, so the claim is that U intersect V prime and W prime intersect, union K complement give the, we're going to have to think about that for a second, okay. So they give the required disjoint open neighborhoods of X and B respectively. Okay, well, let's first agree that U intersect V prime is open in X, because U is open in X and V prime is. Okay, so that's open. W prime, that's open, and K complement is open because K is closed. All right, so they're both open. X is contained in U, and it's also contained in V prime because it's contained in V. So X is in there, they're disjoint open sets. I just need to argue that B is contained in there. Well, B is a union of the part which lies in K and the part that lies outside K. The part that lies outside K is, of course, in there. The part of B that lies in K is in W, and therefore in W prime. Okay, so that's it. So we're done. So the open neighborhoods of X are in capital X. All right, so locally compact Hausdorff implies regular. Questions? Okay. So let's get started on the proof.
How do we know that we can find a W that gets the would be?
That gets what?
Sorry,
So we take W union.
The original W, you mean?
why is it the open set that contains W? Sorry, the open set that contains B intersected with W cover B. So
okay.
what's to say that W prime covers B?
So you're asking about the claim that B is contained in this, is that correct? Yeah, okay. So B is equal to B intersect K union B intersect K complement. Right? That is to say, B is this part, which is that, union with that part, which is that. And then I just observed that, well, B intersect K is in W by the definition of W. Right? So I used that compact Hausdorff implied normal. Normal told me I could choose exactly such a W. And, well, B intersect K complement is contained in K complement, and W is contained in W prime. Yeah. Other questions? Okay. So let me state the theorem. So we give all our function spaces from now on the compact open topology. Then the following statements are true. So given any continuous map F from a Cartesian product of two spaces to a third space, no hypotheses, any three spaces. First claim is that the following function is continuous. So maybe I should, let me make the statement. It's continuous. Okay, so the statement of the theorem is going to continue. But maybe let me flag what is actually saying something here and what's automatic. So forget about the compact open topology for a second. Just suppose I have a continuous map which takes two inputs and gives a single output. Then, given a z in z, I can look at the function which takes z cross x and sends it to z cross x. Okay, that's the Cartesian product of two continuous maps, the identity on x and the inclusion of a point. That's discrete, so that inclusion is continuous. So that's continuous. So if f is continuous, then post-composing with f, that composite is continuous. And what is that composite? Well, it's just a function which sends x to fzx, right? So that's the partial function. It takes an x, it evaluates it with this fixed z, always. That's a function from x to y. So that is always continuous. That partial function is always continuous. That's got nothing to do with compact open topology. So I'm allowed to write down this map without saying anything about what the topology here is I'm supposed to be putting, because I'm just taking this as a set and that as a set. The first claim is that if I put the compact open topology on the right-hand side, that function is not just a function, but it's a continuous function. Okay? So that's the first claim. And the second claim is that the following map is a bijection. Psi zxy. Well, this is just the function which does this, right? I mean, what is this construction? I just described how to take a single function and give you a parameterized family of continuous maps. That's what this board did. It took a continuous function with 2 inputs and turned it into a parameterized family of continuous maps. Well, a parameterized family, as we've discussed in the context of products, one way of talking about a parameterized family is to say, well, it's a function of z. This is describing a function that takes an element of z and gives you the thing which is parameterized by z. That's all that does. That's what the psi is. It takes the f and gives you that parameterized family of partial functions. So that is f goes to, well, I could just write that, but more strictly speaking, it's the thing which takes a point and assigns to it the element of that parameterized family, which is correct. So this is the function which takes an f and gives you the function which takes a z and gives you the function which takes an x and gives you fzx. Right? And the claim is that that is a bijection. It's a consequence of that claim that it's well defined, right? Because this thing over here is continuous, and therefore psi is well defined, and I'm claiming further that it's a bijection. All right, so that's the statement. So let's prove it. We'll start proving it. Okay, so proof. Part 1. Well, there's 2 statements, right? So we'll only have time to prove the first. So the first is that this map is continuous. So let's call it continuity of psi f. Right? Psi f is this map, given the compact open topology. Well, what information do we have to work with? Okay. Well, we know a subbasis for the topology here. I guess that's an exercise I should have mentioned earlier. So remember, if I had a basis, if I had a continuous map, if I had a continuous map from x to y, if I had a function from x to y, and I knew, well, it's continuous if the inverse image of any open set is open, but if I have a basis here, I can just check that the basis elements, their inverse image is open. That's sufficient. And if you think about it, it's also clear that if I have a subbasis, it suffices to check the inverse images of those elements are open. That will imply continuity. Okay. So to prove this is continuous, I just need to take my chosen subbasis there and check the pre-images are open. Okay, so it suffices to check, I mean, this is only a bijection provided X is locally compact in Hausdorff. Apologies. Okay, this is always continuous, no hypothesis. I mean, this map is continuous, no hypotheses on X, Y, or Z, but this is only a bijection in this case, in general. Okay, so to prove that's continuous, it suffices to check that for K and X compact and U open, that the pre-image under psi f of SKU is open. So let me write down what that pre-image is. So that pre-image is the set of all z's in Z such that psi f of Z is contained in SKU. Well, so write that slightly differently. That's the set of all z such that the partial function I get by putting z in the first position of capital F belongs to this collection of functions. So I need to check that's open in Z. well, what have I got to use? I've only got continuity of capital F, so somehow that has to be enough. All right, so that's a set of all z's in Z such that f z k is in U for all k in k. Right, that's what it means to be an SKU. It sends everything in k to something in U. All right, well, that's all the z's such that the pair zk is in capital F inverse U for all k in k. So that's all the z's such that this product is contained in F inverse U. Right, well, that staring at it is not sort of obviously open, but okay, so K is compact, so what are we going to do? So suppose ZK is in F inverse U. So what do I want to do? I want to produce an open neighborhood of this in Z, which is contained in this. Sorry. Right, I'm supposing Z lies in this set. So suppose that Z cross K is contained in F inverse U. So choose for each K in K. Well, for each K in K, the pair ZK lies in there, and that's open because F is continuous. And we have the basis for the product topology given by Cartesian products of open sets. So we can choose an AK in Z, open, and a BK in X, open, such that ZK lies in AK cross BK. It's contained in F inverse U. Right? And that's because F is continuous, so F inverse U is open. Right? Because we're assuming K is compact and U is open, so that's open, and so therefore I can find an open neighborhood of this kind. All right. Well, I mean, K is a compact subset of X, and the BK's give an open neighborhood of every K. So if I take all of them together, they give an open cover of K. And that must have a finite subcover, let's say BK1 up to BKN. Okay. So I claim if you take the intersection over all the AKIs, cross with the union of all the BKIs, that this works. Right, so let's check that this makes any sense. So, well, first, I mean, what am I trying to do? I'm trying to show that if Z is in this set, there's some open neighborhood. Yeah, that's great. So there's some open neighborhood of this guy, which is contained, well, some open neighborhood of Z such that that thing cross K is contained in F inverse U. Well, so that's open and contains K, right? So that, this needs to be I'll stick with what I had. So let's do this inclusion first. That means that's clearly open. So let's do that inclusion. So if I took something in here, so that's in some bki, and if I took a pair in this product, the first thing would be in the bki, so for the I, which the second coordinate belongs to bki, the first coordinate belongs to aki, because that's the intersection. And therefore, by the way this is defined, that pair belongs to the preimage of U. Okay, so that containment is correct. This containment, well, Z is in there by construction, and K is contained in that union also by construction. So that's correct. All right, so we're done. So we've shown that any Z in Z contains an open neighborhood, which is also contained in that set. So psi f inverse of SKU is open, and therefore psi f is continuous. Right, so I'll stop there. So that's the first part. That gives us that psi f is continuous, and then we still have to check it's a bijection.